Hi, I'm Chiming. Today, for my presentation, I'm gonna talk about the smart materials applications in the active food packagings. Food packaging have been developed a lot in the last decades, and the major functions they are aiming at is the protection of the food and the communication with the customers, like until about the foods, the protein content in the food, how long it has been stored, and to become more convenient for customers to use them, and the most basically to have more space to contain the food. And as for active packaging, it is it extension of the protection function. It is to the idea is to extend the shelf life of the foods, and the concept of active packaging is based on the incorporation of certain components, mostly smart materials, into the packaging systems that will enable the release or the absorption of the substances into or from the packaged food, or the environment surrounding the food. And the major type of active packaging materials can be classified into the moisture absorbers, the antimicrobial packaging materials, the carbon dioxide emitters, the oxygen scavengers materials. And then like the package of product shown here, it is able to absorb moisture and also scavenge oxygens to protect the food and extend the shelf life of the food. And I will introduce major types of materials next. So first one, for the moisture absorbers, the most common absorbing system is consists of a super absorbent polymers as the core, and to achieve the function between the two layers of microporous or nonwoven polymers. The product can be a pad as shown in the figure, and there's also another common shape that is a tray of the super absorbents. And this system is good for the ability to absorb huge amounts of water, um, because of the super absorbent polymers, but it's not very efficient with respect to the vapors because of the contact area is limited by the pad shape and the size, and is mostly only one side in the packages. Next, for the antimicrobial packaging materials. The most commonly used are the metal nanoparticles, metal oxide nanoparticles, and carbon nanotubes. Among them, the silver nanoparticles are used a lot for these applications because of its non-toxic. It is non-toxic, and the silver nanoparticles can interact with the surface of the bacterial cells and forming pits on the surface, then penetrating the bacterial cells and damaging the DNA. Also, it can release silver cations, which is also good to the antimicrobial effect. So it is very efficient to kill microbes, but there's also a limitation for the silver nanoparticles because it will need direct contact for the functioning to be realized. As for the carbon dioxide emitters, the idea here is to maintain the inert atmosphere in the package to protect the food from oxidation, and mostly they are associated with the modified atmosphere systems. And most applications are in the meat packagings, like the shown in the figure. The concept here is to balance the carbon dioxide losses due to the dissolution to the meat and the permeation through the packaging materials. The emission of carbon dioxide was triggered by the drip loss from meat absorbed to the emitter pad, and the water will react with the citric acid and sodium bicarbonate presented in the pad, and then generating the carbon dioxide through the reaction. So the advantage for this kind of materials is that they can also have the antimicrobial effect, but the problem is that to control the emission of carbon dioxide is not very ideal. Next, for the oxygen scavengers, the idea presented with this kind of materials basically to reduce their residual oxygens when the food is packed with modified atmosphere systems, and also to reduce the effect from the oxygen permeation through the packaging materials from the outside into the package. So the function is achieved by the oxidation reactions. Either can be achieved by the material itself or the oxidation reaction triggered by the material. For example, the oxidation of organic substances caused by the photocatalytic activity that titanium dioxide nanoparticles can provide. There are also iron particles and the polymers which have the unsaturated functional groups that they can self oxidation could be used for this application. So the oxygen scavengers can help extend the shelf life of the foods significantly, but there are also limitations that the activation agents such as water and ultraviolet light are often needed for the function to be realized. So in the future, lots of researchers are focusing on to put multiple smart materials into one system and to combine the active packaging functions together. And the smart behaviors could be more significantly by reducing the need of activation agent. For example, if the will not the UV light is not needed for the titanium dioxide, not titanium dioxide, for the polymers be to realize the antimicrobial effect. It will certainly become more efficient for the function, and the better protection can be provided by the investigation for specific foods, and contact with materials is needed to become less, and the investigations on the toxicity of material will become an important part for the future development. So recently, Lana and his co-workers developed a bio-nanocomposite of wheat gluten, cellulose nanocrystals, and titanium dioxide nanoparticles with the casting and the evaporation method, and they got very good result. The composite was coated on a craft paper and tested with the mechanical properties and the antimicrobial effect. A significant enhancement on the mechanical properties were obtained, and also the material have great antimicrobial effect. 98% reduction of the surviving number of bacteria were obtained by the researcher. And that's all for my presentation. Thank you.